We could take the largest images in the world with just water, silver, and light. This is what I've been doing.
Strap game on 3. 1, 2, 3, strap down!
Let's start with the basics. A drop of water is a simple convex refracting lens. Until it isn't. A droplet is a droplet because its surface tension pulls its molecules to a center, trying to minimize its surface area. The pulling of the surface tension is overcome by the pulling of the gravitational forces, and the droplet starts to lose its shape. But what if it didn't? If gravity is holding us back from making giant droplets of water,
2 black flags over here.
and turning them into liquid lenses, can't we just go into space? Turns out NASA and I are on the same wavelength. They've been working on this exact project, trying to learn how to manufacture liquid lenses in space, and they have plans to build a liquid space telescope that's 10 times bigger than the James Webb, which by itself was a $10 billion project. It was only 20-something feet folded into a rocket and sent into space. See, I'm not trying to build a telescope, but I do want to take the largest pictures on Earth using these principles. And to do that, we don't need space. I don't believe we need zero gravity flights or centrifugal force. We just need pressure. Like tight pants. Hear me out. You got the junk in the trunk and you put on tight pants. What happens? A sphere. See, a sphere is the most compact three-dimensional shape known to man. So the same thing with the droplet. A droplet is a droplet because the surface tension of the droplet is pulling itself into the most compact three-dimensional shape. We've reached the same conclusion from 2 different perspectives. All I'm saying is that if we want to take these principles and apply them on Earth, we just take the water and we gotta find some really big, tight pants to put the water in. Except the water pants weigh 240 pounds. NASA is betting on the idea that fluid can create an optically functional surface at a scale that would be impossible with traditional glass. And you're reaching a level of physical aperture and light sampling capabilities that we've just never been able to achieve before at a fraction of the cost. So if we want to take the largest pictures in the world, we can't just look at this as a lens. We kind of have to see the whole picture. To do that, we have to understand how cameras work. You have a lens, shutter, and capture sensor. The shutter opens to allow light through the lens, exposing an image onto the sensor. The sensor then stores this light information as a digital encoding, identifying signatures of each pixel to digitally reconstruct the image. Now if I want to take an image and make it bigger than its native scale, size, you scale it, but without increasing the pixel count, you're sacrificing resolution. So better yet, you could use AI to digitally enhance it, or kernel approximation algorithms to digitally enlarge your image, which essentially creates new pixels in your image and estimates its value based on neighboring pixel values. And there's a bunch of different ways you could do this. They all work pretty well, but none of them are perfect, because at the end of the day, this is artificial information. You're using estimated guesses to enhance a picture. When you enlarge an image, you're not creating new optical information, you're just taking the existing information and having it occupy more space. There's an optical footprint to an image. The aperture was captured through, the distance, the angle, the amount of the light field the lens was able to capture. These are all things that are intrinsic to an image. They scale with the image, they're part of its character. So there's an information ceiling to a picture, just like a fingerprint. You can enlarge a fingerprint, but you can't make it more than it was. You can't learn anything fundamentally new about that fingerprint or that person that it belongs to. So just like a fingerprint, if we want that information and the character that only comes with scale, we can't take small pictures and make them bigger. We have to take bigger pictures in the first place. The question becomes, where are you going to find a sensor capable of storing that much information? if you're looking to take pictures that are like feet by feet big, because modern silicon sensors only get so big. And that's when you're going to find the LIST, or the LSST, the world's largest digital camera at the Vera C. Rubin Observatory in Chile, which cost $168 million with 189 individual sensors stitched together into a single 23-inch, 3.2 gigapixel focal plane. The front lens alone is over 5 feet wide. Look, I don't have that kind of money or time. That would be cool, but instead of getting a bigger sensor, I turned to analog photography. Analog doesn't store information as bits, but as submicron particles of photosensitive silver, less than 1/25,000th of an inch on paper. In comparison, a human hair is only 70 microns, and an ink dot on an inkjet printer is usually 50 to 100 microns. In analog photography, the paper becomes the sensor. We're exposing onto silver particles that are smaller than the coronavirus. So we don't have to manufacture a giant grid of modern sensors, and there's no technological limitations. If we want a bigger picture, we just get more paper, and a bigger lens, and bigger bellows, and a bigger camera system. People like Ian Reuter have been doing this for a while. They've been exposing onto 200-pound pieces of glass, turning trucks and houses into giant cameras. And they've all wielded like the same tool, the same 2-inch large format lens. And we've mastered in analog photography everything around the lens, but we've never really questioned the lens too much. And that's where the photo gets bigger, literally. We're able to capture that information and the character that comes with scale, and we might be able to push this to a whole new level with pressurized fluid optics. What we've been hoping to do is build a camera large enough to take pictures where we can see the world at its true scale and a truer light in a way we've never been able to see it before. So that's what I've been working on. I appreciate you listening. I hope you can follow me along on this journey. Next week, we're gonna introduce some people that were really important in the making of this lens over the past winter, and we're gonna talk about our whole experience and what that was like. It was a serious challenge, and it pushed all of us to our limits. Of course, I'm going to go into the math and the physics and the theory behind it, and kind of design for the next steps, testing and taking pictures. And if you think that we don't actually have a subject, so if you know of a subject, or if you want to be a subject, or if you have some great idea, something that we can take a picture of with this camera, please let us know. We're starting with 7-foot by 8-foot photos, and that's only because of limitations we'll get into in future videos. But also, this is a series extending beyond the camera. I have several other projects I've been working on over the past year and a half, and I wanted to put it out there just to share it with people, because I feel like there are so many awesome people that I know that I don't really get to connect with, and I want to share it with them, and I want to share it with anyone else that might be interested on the internet, and hopefully meet some cool people that way too. So thank you, and hope to see you in the next video. Have a good day. Yeah.
Pretty good.
Yeah. Thank you, dude.
Glad you